especially with the especially with the devices when they are connected as a network, they can provide you an environment monitoring, direct environment monitoring in smart cities or in a workplace. So as I said, the base material for my devices is graphene. Graphene has been detected not in 2004. It was just isolated from the graphite in 2004 by two scientists, Professor Andre Geim and Novoselov. Since then, there has been a gold rush in 2D materials and graphene. So if we look into that, since 2004, there was a slow increase in the number of articles and number of patents, but after the Nobel Prize, there has been an exponential growth in graphene and graphene related materials. So whether graphene, using a graphene as a material for engineering, or maybe a graphene to replace the current electronics. So what we can see that it impacts the entire world, and especially with the countries like India, China, US, and European. So there's a lot of research going on, graphene and graphene related work. There's a tremendous number of applications which we could figure out, and that also makes, for many of the young students and researchers to look into a research topic in such. This has been explained in many presentations and also in through thousands of research articles that graphene is a wonder material with superlative properties. Like the strongest material might be a 200 times stronger than a steel, but you should not confuse with this. When you compare steel atom, single atom thick film of iron atoms and graphene, then you can say that graphene is the strongest material compared to even iron atoms connected to each other. But it's a single atom thick. We should not get confused with this statement. But yes, when we compare at a single atom thick level, then it's the strongest material, highly conductive. Mobility is very, very high. Yes, of course, the large surface area, superior chemical and mechanical properties. We'll definitely look few of those when I go through my own sensor technology. But what is most important to take away from this slide is that the graphene doesn't have a band gap. So anything which doesn't have a band gap, so far as our existing knowledge is that we cannot make electronic switches out of this material. So graphene cannot replace the silicon technology which we are using in order to make electronic devices, because all these devices work on some sort of a principle where you can stop the current in one direction and let the current flow in the other direction. So that requires a band gap, but graphene doesn't have a band gap. Recently, there's a lot of research going on where they try to create the band gap in graphene while having a mechanical change in mechanical properties, or while functionalizing it with some sort of material, which means chemically you can modify the graphene in order to create a band gap. But again, it's very difficult to replace the existing technology with some sort of a chemical modification or a mechanical modification of graphene to make these electronic devices. But yes, still we got a graphene to work for a lot of applications. All right, so when I say like suspended graphene arrays, which I use for my gas sensors, potentially can also be used for biosensors. So why, the question arises, why the suspended graphene? Because graphene is a single atom thick film. As soon as it gets onto a substrate, whatever contamination is on the surface will affect the pristine properties of graphene. So there's only one free charge that is available for electrical current. As soon as it lies onto the surface, which may be a dielectric in other sense, but all the contamination on the surface would become a scattering sites for it. And at the same time, other contamination can also dope the graphene from its pristine property. So the original property of graphene, sort of affected as soon as this goes on a normal surface. That's why we need to remove the surface underneath so that we can take the pristine graphene properties. For example, if we see in the picture on the right side, there's a graphene film connected between the two metal electrodes, and there's no surface underneath. So it's a freestanding. So when it is freestanding, you got all those high quality, mobility with 150,000 to 200,000 centimeters square per volt second mobility. And of course, we got to double the surface area. So there's a surface on top and surface on bottom. This is very important for interaction with the biomolecules or gas molecules in terms of like sensor technologies. Also, because of the no interaction from the surface, no scattering sites, there's a high conductivity between these two electrodes because of the graphene. Graphene's high electric. So suspended graphene provides you a lot of applications when you want to do a very, very high sensitive biosensors or gas sensors. But there are challenges. You cannot make a large number of suspended structures because this is a single atom thick film. As soon as the area or the length of these strips would go bigger, they will sag down and will touch the surface. So it's very difficult with the current traditional method. You cannot make large area graphene suspended structures. And also it tears off because of the water adhesion. So what we come up with the a new methodology in order to suspend in order to get a high yield in the suspended structures. We come up with a 10 millimeter square chip, which is basically a small chip that you can use in order to make the tiny micro devices. So on this 10 millimeter square or on 15 millimeter square chip, one can make a large number of microchips, which are like, say, for example, 3 millimeter square area. And on these, you have a large number of devices. So each device would appear like this: two terminals, metal lines, and then graphene is suspended over the cavities. So these cavities are done inside the substrate, and then graphene is just lined on top of these cavities. So it looks very simple, but it's a single atom thick. It's very, very difficult to suspend it over because it breaks as you transfer the graphene onto the surface. So anyway, we got a good results with the methodology that we protected it later. This is just optical images of a chip with the 15 millimeter square as a starting die, and then you have one chip, microchip, which is around 3 millimeter square. And on this 3 millimeter square, there's a lot of devices. So you got like a 180 to 200 devices on it, which can be connected serially, or which can also be connected in parallel in order to just give you an averaging at the device level as well as at the chip level. So simplest way of making such devices, you start with the silicon oxide substrate, and then you create cavities through a RI system, a dry etching system, and then you transfer the graphene film stack. So this graphene film stack comprises of a graphene underneath with the polymer, which is patternable lithographically, and then there's a metal film on it that provides some sort of like strength to the polymer. Otherwise, the polymer breaks. So it's slightly different than the traditional method of transferring graphene with the PMMA. So this is just how does it look like when it goes onto the cavity. So it sags a bit. That's why we need to keep the depth of the cavities around 1 micron, where the sag can be up to 150 to 200 nanometers. So it doesn't touch the surface. So once you have a graphene, you create the metal lines on top, and then you can release the polymer or the protecting layers in order to have a graphene film on top of the cavities. So I might skip this. This is just a copper film with the graphene on it. So we transfer polymer, and then we do a aluminum deposition around 25 nanometer on it. So this aluminum provides some sort of strength to this brittle polymer. And then once you etch the copper from below, and then this graphene is ready to be transferred onto the surface. So this shows us an SCM image where you have this 9 millimeter square chip. So this is 9 millimeter square chip at the moment, but it can easily be a 1 millimeter square because lithographically it's all possible. And then you see an individual device. There's again same cavities in silicon oxide and a graphene on top of it. So SCM images where you see a bright portion, they're just a charging, which means like there's no graphene. And there are some areas where you see this graphene. So this picture was picked just to illustrate that where you will find a graphene on fully covered by the cavities, or where you don't have a graphene. So if you will look, a closer look on one of these devices, so you can easily see a very thin film going on top of these cavities. So this is 1 atom thick film, and it tears off at some point because all these things are done at a sort of like in a wet statement. So in a wet form, it always comes up with some sort of tear. And this is also depends on the quality of graphene. So you can easily see this graphene film is lying on over the cavities. And if AFM image just also tells us that the cavity depth is around 1 micron, and when graphene goes on top of it, it just sag around 150 nanometers. So there's a pretty flat membrane. This what particularly, when you do a Raman spectroscopy, you can identify the points where the graphene is suspended and where the graphene is supported. So it's very important to understand that, what happens when the graphene is without the surface and it's freestanding, because then you do not have those, unwanted doping from the surface or any sort of like, scattering that comes from the surface contamination. So, this is further Raman spectroscopy just to show that, we have a good area of suspended graphene than the supported graphene. So as I said, like it's very difficult to have 100% yield because this all depends on the graphene properties. But with the methodology that we used and then we protected as a know-how, as a patent, we could get up to like 56%. So idea is to get 100% yield, but that only comes with the high quality graphene. And what happens, like, when we have a graphene suspended and supported, so a suspended graphene will have a reproducibility in batch to batch and, a number of devices when you move from one batch to another batch. So this is very good news in terms of going for a large scale device fabrication. Otherwise, when we do a work with the graphene, there's always possibility that one device will be different than the other device, which can easily be seen with a graphene on a supported substrate. So this is suspended, you see a probability. Also the resistance is very low, around 1 kilo ohm resistance, whereas with the supported, there's a large change, and also from batch to batch. Each bar tells us about the resistance measured from 10 devices from one batch, and then you have like 7 to 8 or 10 batches. So there's a lot of variability in supported devices. So that's why we fixed our technology towards the sensor array. Now comes the testing time. So once we have device, now it's a two-terminal simple device, a resistor made of made of graphene channel. And since, as I told, that the graphene is just like a carbon atoms connected in sp2 hybridization, is a free electron available, and these free electrons can interact with the external gases. So either can reduce the, these external gases can reduce the graphene or can oxidize it, means it can change the properties while doping the electrons or doping the holes in the graphene. So you can see a change, positive or negative change, when we have interaction with ammonia or nitrogen oxide, or even with the carbon monoxide. So graphene is sensitive to different gases, but it cannot identify that what is what. So for example, there's a negative change for carbon monoxide, as well as there is negative change for nitrogen oxide. So it cannot identify which one is which, but we can easily see that there is a change when the gas interacts with the graphene. So now this gives us a sort of a motivation that we can move from a non-specific graphene based gas sensor to a selective gas sensor forward. That's just a sample how we can do this. All these things we do in the research laboratory, sort of like a rudimentary type of small work in order to get the sensor start working. So what was the important in order to make a selective gas sensor? We need to functionalize the graphene. This is called functionalization, but in a normal way, we say like we have to coat the graphene with some sort of material where it can only interact with the specific gas molecules in the environment and then leave, not interact with the other one. So interaction of these, sort of like a bluish dot that goes on to these green coating film will give us a different sort of sense that it's not detecting any gas, but a specific gas. So that's what we would like to see as a personal sensor. If I am at, sitting in my home, I'm worried about the formaldehyde concentration that comes from the carpets and comes from the furniture or the wooden stuff. So very carcinogenic, and I would like to know that what is the concentration of formaldehyde. That's why what we did, we functionalized the graphene with the TFQ, tetrafluoroquinone, which are very selectively attached with the formaldehyde in the environment, but it doesn't interact with the other gases in the environment. So if we have a functionalization of graphene with the TFQ molecules, then we can use it as a formaldehyde gas sensor. So this is just a XPS data that tells that when we have a TFQ film on top, then we start seeing some presence of fluorine molecules, and these Raman spectra just tells you that there is no much change before and after, because we are not doing covalent bonding with the surface. It's just non-covalent functionalization. So those who understand the functionalization with graphene easily can detect. So again, I said, when we do all these experiments, we really don't need a high-end, system or tools. We can just make our own rudimentary sort of, chamber where you can test your sensors. So what you see here is a small PCB with a chip inside and some sort of like, electronic components connected. And then we had this humidity logger as well as a multimeter or a data logger connected to the sensor output in order to just see that what happens when you inject a small amount of formaldehyde inside it. So if you see, this is the injection syringe. So when you inject small amount of formaldehyde mixed with the water inside this chamber, and then you blow the chamber with a slot heat, then it evaporates. And then when it evaporates, it diffuses through the chamber. So when it diffuses through the chamber, it interacts with the surface of graphene, which is coated with the TFQ molecules, and can give you a selective detection of formaldehyde. So all the concentration of formaldehyde might be very high, because around 1 ppm, 1 to 10 ppm is very, very dangerous, if that's available in your environment. But these were the early tests where we just want to see the efficacy of the device to identify, whether it detects the formaldehyde from different availability of the other gases also. So that will be shown in the control experiments. But what most important with the graphene based gas sensor is the recovery of the sensors. So generally what happens, like, if you look into the existing technology like metal oxide semiconductor, so if we want to recover the sensor with, whatever deposition of material goes on it, we have to heat it, at a high temperature. At the same time, we need to pass a high current. But with the graphene based technology that we use, we could only use a small, low power UV irradiation. So this low power UV irradiation will easily make your sensor to recover. So what happens, this UV affects the bond between the TFQ molecules and formaldehyde, rather than breaking the TFQ from the graphene, where they are anchored to detect the formaldehyde selectively. So when the same concentration, you can say that the sensor recovers as soon as the UV light is switched on, right? And as if we do not expose it with the sensor starts recovering, but the recovery is very, very slow. So if you see this through the blue line, it would have recovered like this, but when you eliminate it with the UV, the recovery becomes faster. So this is suspended structure and this is supported structure. Yes, supported structure also shows selectivity towards the graphene, towards the formaldehyde. But look at the distinguished, it easily distinguished with different concentrations, whereas the supported graphene just behave on its own. And on the other side, the recovery of a supported graphene is not as good as your recovery of your suspended arrays, because when you eliminate the light, the underneath, whatever is under the graphene and the oxide will get permanently, charged up, and it will not give you a full recovery. Rather, it will dope the graphene on the other side. So that's why we do not use, this just shows that, the graphene sensor with the suspender structure is much, much better than graphene sensor with the supported structure. So these are just analyses where we can get all those, figure of merits, that what are the sensitivity, what are the concentration of the detection limits. So as I said, when we did with the TFQ, we really wanted it to only detect the formaldehyde. It should not detect the other materials, because that's what the purpose of a graphene selective gas sensor. So what we did, we exposed the same chip, functionalized with the TFQ molecules to ethanol, toluene, and even the relative humidity. So we, humidize the chamber. Well, we see that we do not see any change in the sensor response when you increase the ethanol concentration from few, ppm to around 200, 1800, 2000 or 1800 ppm. The sensor doesn't respond. Similar with the toluene, and there's a small, jumps with the humidity, but it doesn't show much as it shows the change in concentration of the formaldehyde. So that proves that the sensor is selective to TFQ molecules, selectively picking up the formaldehyde from the diffusion chamber, and it was insensitive to any other gases. Whereas we also did with the, when we do not have this suspended graphene structure functionalized, they interact with the toluene proper, in a good way, as well as with the ethanol and with the relative humidity. So a sensor functionalized with the TFQ does not get affected with the toluene, ethanol, and relative humidity exposure, but a sensor without any TFQ interacts and provides your response. So that confirms the selectivity. So as I said, these sensors are in a micro scale at the moment, 3 mm square chip. What each individual device is around 100 micron by 100 micron. We can easily transfer this technology from 3 mm square to 1 mm square with one chip, with one device, like few hundreds of few hundreds of micron, so that we can easily integrate these tiny chips with our mobile phones. If we want a very personal gas sensor or air quality monitoring in home, it can just come as like a small dongle or some sort of a substitute that can be connected with your network at home and can provide you a data. So assume that you have a network of these sensors, can be easily connected to the street lights in a city, and then it can collect the continuous data throughout the day and throughout the evening, and can provide you a valuable information, whether what sort of like interventions we need to do in order to control the pollution within the city. For example, one can take a decision that whether we should allow the traffic during that specific time of the day in this direction, or we should divert divert the traffic from that. So similarly, something which we found in the city of London, that during the daytime, it's expensive to go inside the city than park the car outside, because the pollution that is done only to reduce the pollution during the daytime. So similar things, similar policy decision can be done when we have a lot of data collected through all these networks, and then we can do some sort of like government policies to control air pollution in the city as well as in homes. So that's it. I'm still working on this. It's still a prototype tested in the lab, and we need to take it to the full environment, open environment, where we can check its efficacy and usefulness for open environment. And also, if we can integrate it with the mobile phones, so that it becomes like a new technology with the upcoming mobile phones. So that's my group in Manchester. I really like to thank everyone who helped me, especially Dr. Max Migliato and Professor Young. The group I was working, few of my friends, from the Department of Material Science, Earth Science, and Biotechnology, that was a part of the research project. Right. Thank you very much. If you have any questions,